So, hi everyone. I'm going to talk about reactive and the style of reactive programming. So, what's the deal? Maybe if you're like me and you've seen on Twitter or elsewhere reactive this, reactive that. Now, Java 9 includes the Flow API in java.util.concurrent, which is all about reactive. And well, what is it? And that's what I'm going to try to tell you during this session. So, reactive is all about scaling. It's one possible solution to scale horizontally or vertically. So that is like using your resources from your own computer more, or adding machines to scale horizontally. So, what's reactive? Well, the thing is, reactive is a lot of things, because there is kind of a terminology overload. First, there used to be in the old times something called reactive programming, which is a subset of data flow programming. So you would say A equals B plus C. If B changed, A would be automatically updated, and that would be something supported by the language. But you know, as things are, sometimes a word like reactive sounds nice, and someone comes and says, oh, I want that word as well. So it's not exactly what we're going to talk about. So I won't use reactive programming as a sentence. If I do, I will slip. You can do reactive programming with the kind of patterns that I will describe, but that's something else. So then you have reactive systems that you also may have heard, and they're also something different, but a bit linked. So it started with the Reactive Manifesto, which was some kind of PR operation from some guys to say, look, let's do systems better. But if you look at how they define better, no one can disagree. We want the system to respond, to stay resilient and elastic. Who can disagree? And they're a bit more of opinion when it says it has to be message-driven. But that's not also what reactive code is. That's when you're talking about systems. And maybe if you use reactive code in all of your system, then you're going to have a reactive system. But still, these are different things. So what's reactive as properties? If I have a library and I can say it's a reactive library, well, it's a library that gives me some kinds of guarantees. It tells me I'm not going to be blocking, so we're going to see what it means. And it's handling back pressure also in a non-blocking way. And another thing is that it has explicit error handling. You don't want to have these errors not managed in the domain model of what a reactive is. So how did it get started? It started with the reactive extensions that were first for C# and JavaScript. And then there was some kind of update on it from other guys as well, called Reactive Streams, and that's what became the Flow API. Like they took the definition from the Reactive Streams initiative and put them in Java 9 in java.util.concurrent.Flow. So, first, if I'm talking about what is non-blocking code, let's see what's blocking code, what blocking is. So, this is the kind of code that we have when we write maybe a REST controller in Spring or in JAX-RS, or it can be code that exists wherever in our application code as well. And you're going to see that the method signature is what we're looking at. Here, I'm returning a DTO, and that DTO, because of the semantic of the Java and the JVM, that method is going to be called on a thread. And when you go out of that method and you go back one step back in the call stack, the DTO has to be there. So if that DTO requires remote information that you maybe need to go across the network to build, if you need that information, the thread has to block. There's just no other way for it to go. So basically here, my repository that is handling my business logic will also block, and I can't do anything about that. So that's what we are used to, and it seems really nice. So what's going when the framework is calling you? Well, you are getting called on a given thread. your code is going to block. And if your code doesn't do remote I/O, if my DTO is entirely local, like in memory, no problem, gonna reply. But most of the time, the code looks like this. I'm doing a DB query. And that DB query has to take some time, I mean. And the thread is going to be blocked for some time. That's fine if you have many these threads, but if you have a few, not fine. So it seems good, because we used to reason that way. And we can mix I/O, we can mix state and effects and local computation. That's very cheap. So like these are completely different cost models. So it's simple because we're used to do that. And also we have tools to debug it. Like you plug in Eclipse, you see your nice stack frames, you can see where you called from. It has some performance benefits if you have what you want is latency, so the whole stack is optimized for synchronous method calls, so you have low latency on those, but it's really not a big difference. But first, and the worst part is that he assumes that you're returning on the same thread. And it is contagious. Why is the framework written that way? Why is Spring giving you that programming model? It's because above Spring, there used to be Jetty or whatever they're using. And if they were using a blocking model, there was no point for them to provide us a non-blocking model. So we've been contaminated by them. And in turn, we are contaminating our own code to avoid, the code below us, take other choices. So basically, we've been blocking, and we're blocking everywhere. And maybe it's not such a good idea. So where does this come from? It comes from the request execution model that we have. And requests, it can be HTTP requests, but it can be Eclipse when I click on an item, or like on a small logo, and it starts something. And the question is, how can I handle many requests, like 10K requests? And I want to keep responsive, so whether my server is still up as far as it can, or maybe my UI is not frozen. So when you have a UI frozen, basically you're making the UI threads busy, and that's and blocked by some I/O often. Those are the same kind of problems. So it's not necessarily only about networking. So it comes from where we come from. In Unix times, and we had this coordinator process. It came with the connection. It would spawn a new process, and that process would handle that session, and it could do in a blocking way because there was not a lot of sessions, maybe a few, but okay. Then threads came, and we kept the same model. We were in one process. Instead of spawning new process, we spawned new threads. Or maybe we pulled them, but it's the same at the end of the day. So the C10K problem came, and it says basically, what happens if I want to hold 10K connections at the same time? What happens if I want 10K requests at the same time? So the guys looked at what happened, and it turns out that there is a bottleneck. If you have many processes at the same time, or many kernel threads, they cost a lot in memory. It's harder work for a scheduler. And there have been approaches to mitigate the cost of this, but it just doesn't work. So reactive is about finding ways to say, OK, we're going to scale, and we're going to reduce drastically the number of threads. So the question kind of became, so how many threads do we want? Well, we have now computers with several cores. So to exploit their parallel capacity, we need at least one thread per core. That would be great. The thing that what we saw is that I/O dominates everything. If going to the latency of my L1 cache on my CPU is 1 second, going to the disk is going to take months. Going through the network is going to take years. A packet from California to Netherlands takes 10 years. So we need to find a way to set I/O aside in a way that it doesn't block our threads, and that we can benefit as much parallelism from our CPUs while still having very few threads. So turns out that in the JVM, it has been for a while, there is non-blocking I/O. and it's obviously wrapped from what the kernel provides. And the idea is that you tell the JVM or the OS, do that operation, blocking operation, but don't block me and tell me when you're done with the data that you've retrieved. And so the data is called back from another thread. And we kind of have to handle the way that this is a continuation of what we asked earlier. So it becomes a bit tricky to manage, but still we have the right semantics. If we have non-blocking I/O, then it's our application that becomes a bottleneck, because we had a blocking application on top of blocking I/O. So now we freed the lower level issues, but we're still writing blocking code. And the problem that we have is basically we are not getting the most of our system. It's still blocked a lot, and we can maybe still spawn threads at that point, but it's not the solution that we want. So what we would need is to use the same callback approach that non-blocking I/O had, but for our code. So these are the non-blocking idioms. And we go back to the blocking code that we had earlier, and to change it to being non-blocking, a simple solution could be to add a callback. It would look like that. When you're done, repository, call my own result callback, and obviously the framework will understand that this on result has to be the place where the result is taken from. And you see now I return void. So I'm saying basically there's no point to wait on any return value, and the thread can just go. So that's one solution. Actually, it doesn't capture errors. So if I want error handling, I need to have another listener for when error happens. And we see now that throwing exceptions itself is a blocking behavior. It's part of the blocking behavior. So not only the return value, but the exceptions are both blocking things. So that paradigm, that way to write code, it's called CPS, or continuations, passing style, or callback hell. And it has the right semantic when you want one value, but it doesn't scale in the code. It becomes very verbose, very hard to read. So, and it poorly composes, because everyone has their own semantics, their own callback. Here I use a consumer, but someone else has their own callback, and I can't compose them easily. I have to write that glue code every time. So there are solutions, and I mean, we use them in Java 8 maybe, so futures and promises. So basically the idea is that let's make this continuation, let's make these two callbacks, let's make them data structures. And the semantics are a bit different, but just as powerful, and you can go from one to the other. And what's interesting is that you made these abstraction of a continuation into a value. So we return the future, and we don't need to have those callbacks on the side. And we can express the code we're used to with dependency on one line, then another line. We have some kind of flow in the code, and we won't say, first I do that, then I do that, then I do that. We can do that because it's a monad-like structure. So it just says that we can work on values not yet ready. I'll show you that in a moment. So this is implemented in Java 8's completable feature. That works, but it has an API surface very, very big, and it's a bit ugly. So Osgi has a promise API that has the same functionality, but in a more elegant way, and JavaScript as well. So that would look like that. I'm using the Osgi promise API here. Instead of having those callbacks, and instead of returning the myDTO in the blocking way, I return a promise of myDTO. And the thing is, now I can immediately build that promise object, because it doesn't depend on value that doesn't exist on the stack right now. It depends on those callbacks. And that's something else. So you see we get the same kind of style, because it looks like we're returning the value, except we're returning a promise of value. So we made that kind of paradigm fluent. And that's a small excerpt of the promise interface, not much bigger, but the main things are the onResolve, which says, it's not exactly that, but it's the same semantic, which has the CPS equivalence, which says, if that promise is finally satisfied, what do I do when it goes well, or what do I do when it went wrong? And then you have these then functions. They're called map, like in optional, for instance, java.util optional. Map says, okay, if I have a promise of an x, and you give me a function x to y, then I give you a promise of a y. And flat map does the same thing, but it can flatten another promise. So if I had a promise of bread and have the promise of eggs, maybe I can make crepes from them, right? But I can only make a promise of a crepe, not crepes directly. I cannot escape the promise, not without blocking, right? So that's what it looks like. If I'm in the blocking style, I can get the full name. So I'm calling the repository. I asked for the first name. It takes time. It blocks. My thread is blocked. Then I get the first name variable. Then I call the last name. I call the repository. It takes time. Then the last name variable gets on my stack. And then, okay, I have those variables. I can add them. So get full name took at least the time that get first name plus get last name took to execute. If I use a promise, I call the repository, it gives me a promise. So it's immediate. The promise it's built, it's going to be able to notify me when it's ready. Same goes with the last name. So far, no time has been spent. It's been like super immediate. It's not even on the same order at all that's blocking. And then I use those flat map and map, which says basically, if I have the two, join them together and give me a promise of those. So this is a bit hard to read, but what you must get from that, first you get used to that kind of programming, but the most important is that the getFullName method itself took no time to execute. And the thread at no point was blocked, not necessarily blocked. Okay, so since this is a bit difficult to read, some languages propose syntactic sugar on top of that. That's what C# does, that's what JavaScript does, and Kotlin. So they have these async methods. If you annotate a method as async, then it will be able to give you syntactic sugar to make those promises look like blocking code. You just have to say await on a promise, then you can use the value as if it was blocking. But this is just syntactic sugar that will transform into the previous code that we saw, if the compiler supports that. So it's not supported in Java, and it's not in the plans. But Kotlin has it with suspendable functions. So, all right, these are promises, but it's like the first step in Reactive. What's next in Reactive? What happened? So it started with Rx, and promises existed, but it worked with just one value. You have the promise of an x, and not of x's, of a bunch of things. So we would like to extend that model with multiple values. So we could have a promise of a list that would return multiple values, but that would mean we know exactly how many values there are first. We have to know that when we create the list, and we have to also have all these DTOs in memory when we do that, which can be expensive in terms of how many memory is consumed. So that's not working. So let's go back to CPS and see what kind of semantic we kind of want to capture. And we want basically onResult to be able to be called several times to tell us when it's complete. So when you're done giving me DTOs, then call onComplete on me. And if something happens and that's wrong, call onError and it's done. That's a bit what we want. And the same way we had promises for single value CPS, Rx gave it as RxObservable. It's a mix of promises and streams, in a way. And it's advertised as a way to replace the whole observable pattern in a way that is more suitable to non-blocking programming. So what Reactive Extension did around that and other things is do a lot of groundwork in the concepts, in the terminology, the design, and some tools. And I will show some of them now. So first, it's event-based, so they define the events that we just saw now as callbacks. So if you have a next event, you get an element. If you get an error, it's the end of the stream, and you get the error. And complete is a successful termination of the streams. Sometimes they're called signals. All right, and one nice tool that they gave us is these marble diagrams. So each line here represents an observable stream, and the circles are values. So you may have an object that says color and value, and one is green with 20, then 40 yellow, and so on. The straight line represents termination of the stream, successful termination of the stream. So here you have two streams, and they also gave us operators, which are functions that take observables and can work with them. So you can define your own observables if you like, or you can, well, they provide a lot. And the merge operator will simply merge those two together. So that is extremely powerful when you can use and reuse constructs on top of these data structures. That's really smooth when you program with. So how would that work in the code? You would say maybe have an observable with 1, 2, 1, 3, 5, another with 2, 4, 6, and I merge them and subscribe to do something when something happens. So actually, that doesn't match the previous example, because those observables, you see, I created them just now. If I merge them, it's going to be 1, 3, 5, 2, 4, 6, because they're not flowing concurrently. I'm just defining them now. It's not like values that come. And something else that they gave in terminology is this notion of hot versus cold observable. So what we had in the example was a hot observable. It was sending events no matter what, and so it was parallel. In a cold observable, it's only triggered when someone shows interest, and only that someone is going to get the values. Then they added some more IDs. It's single value observables. What if we expect only one next event? And here, observable meets with promises. It's like an observable of 1. There's a bit of difference because observables are always lazy. You always have to subscribe, while promises start usually when you create them. And there is also a slight difference in semantic whether what happens if there is no next event, like if it's empty or if it's an error. So that's the difference between single and maybe. So okay, that's a very short overview of Rx. I don't want to go into Rx. I'm just saying that because they made a lot of, give us a lot of concept to build on. And that's what the Reactive Streams guys did. They built on those concepts and expanded them, because turns out there was an issue. What if there are many signals? What there's a lot of on next? What if the producer is sending a storm of events? We can't block because we're never blocking. So we have a problem. A machine gets overutilized. Maybe we want to buffer. It's going to fill the queues. We're going to go out of memory. Maybe it's going it's not going to go well anyways. So what could we do besides blocking? Well, we could buffer. It would work with bursts, because maybe on average we can process all the events that are sent to us, because it takes like 10 minutes to process, but there are short bursts of 2 minutes. And so these bursts can be managed in the long run. Or maybe we have to drop and say, sorry, but we're ignoring what you're sending at us. Or maybe we can say, oh no, you're a bad boy, we just closed the stream. But why did we want to block? The first reflex to block, because we are used to the fact that blocking throttles the producer. We want to throttle the producer. That's really what we're trying. But if it comes for free in synchronous programming, when you go to non-blocking, it has to be made explicit. You need a way to tell the producer, okay, go down. And in reactive streams, you don't say slow down. You say give me whenever I ask for you. So you signal the producer if you're ready to receive data. And you can say, I'm ready to receive more than actually is true, because that's going to be your buffer. But that's the idea, and it's inspired by TCP. So not everything can be back-pressured, like keystrokes. If I'm writing very fast on my keyboard and it's not being followed, well, the keyboard can't allow me not to press those keys anymore, right? Maybe I'm going to have some visual feedback. the PC is crashing or something, not non-responsive, and I'm going to be back-pressured into stopping. But some things, like the temperature outside, just cannot be back-pressured. So in those cases, we have to buffer or drop or find another strategy to subscribe, maybe get fewer events. So this is a canonical example of back pressure. A client or clients are asking to download very large files through a proxy. So they have a bandwidth to the proxy of 15 megabit per second, megabit per second, sorry. And the proxy with the server can go much faster, 1 gigabit per second, right? So if I download this very large file, maybe I'm going to be the client, I'm going to say get the large file to the proxy is going to be to the server get the large file, and then on the link between the server and the proxy, the server is going to be able to send very fast the contents of the file. But the proxy won't be able to do so. It won't be able to restitute that file at the same rate to the client. So it would have to push all these chunks of content into its own memory. So if the file is very large, it's not going to work. But let's keep in mind, we have hundreds of clients at the same time. It's never going to work in any case. So the proxy has to find a way to ask the server, go slow. And TCP can handle that. In TCP, if you don't ask things, it's going to reduce the window and it's going to reduce the transfer size, the transfer speed. But how do you make that happen when you're in Java and you're using non-blocking programming? If you have blocking I/O, it's going to work out of the box because the input stream and output streams that you use are going to take care of that. When you go to non-blocking, you have somehow to bridge that non-blocking back pressure to TCP, and that's something that can be done. What we see here is that, in a way, back pressure composes the slowest consumer is able to say in the pipeline, that's how far I can go, and it can be, you know, repercuted in the whole flow across the streams. So reactive streams, that was a specification, an API, is basically non-blocking back pressure aware streams. It came from, it's a new take on reactive extensions that was meant to include different frameworks in the reactive spectrum to interoperate, including ReactiveX, RxJava, Reactor, and other projects. And now in Java 9, it made it into the JDK. So it's known as Flow. The publisher in reactive streams is the interface that is like the observable in Rx. It's a very simple interface, but it gives just as little as it can to give you non-blocking back pressure. And if you want more, you need to use another framework on top of that. And the way it manages back pressure is to signal explicitly when you're a consumer how many elements, how many units of work you are ready to accept. And it's up to you to define what a unit of work is. It might be, so obviously the type that you're going to get, MyDTO, but if you're on a network on the previous example, it's going to be a byte buffer, but byte buffer doesn't say a size, so you could say it's going to be a byte buffer of 2,000 bytes or whatever you want, right? So reactive stream is very crude. It's only made to interoperate. It's only 4 interfaces, 1 TCK, and a spec. So these are the names, publisher, subscriber, and so on, of the interfaces. And there are many implementation pitfalls. For instance, first, you never can block, you never can throw an exception except null pointer exception, and a bunch of other things. So it's not a good idea to try to implement these on your own, and you should rather prefer a framework. And those frameworks, or those libraries, are very small. I mean, they're not necessarily bringing a lot of garbage in your code, right? So it also makes these different frameworks which implement this interface compose the back pressure between them. So if you have, I don't know, Akka, Reactor, RxJava, maybe some wrapper on Osgi push streams, all of them should be able to compose, and the back pressure should be able to push back, basically. So we've gone from the threading models that we had before, fork threading model or threaded request model, sorry. So the reactive request model is a model where you don't need a number of threads. You're sharing threads. You're collaborative, and the number of requests should not affect it. So it's not a one thread per request. It's whatever number of requests. As long as your machine can handle it, it's OK. So it's great for servers, like Spring is going to non-blocking, like reactive, webflux, whatever. But it's great for any kind of programming. And if you have a library that you want other programmers to use, it's a sort of property of your library to tell me, as a user of your library, I'm not going to hog your resources. I'm not going to block your threads. I'm a reactive library. I don't care exactly what kind of API you use. You can use CPS if you like, as long as I can bridge it. And it's a way that I don't need to have a thread pool just for you. So in Eclipse, for instance, the jobs API could bridge to something like that. It's a bit the same. So what we get from reactive, non-blocking back pressure. So lower scheduling overhead because we have fewer threads and less allocation, less context switch, and we get more utilization of a machine. There are cases like at work. We went on a program from twice as fast from going to blocking queues to reactive. So obviously, a lot of things like non-blocking queues exist outside of reactive. We could do that, but it was very easy. The code has been very simple because you get the right concepts, and there has been work on making it simple to use. So overall, you get higher throughput. There is another example that is online. The Black Friday, some guys changed a cluster of 60 machines by two Akka systems and had better latency and less crashes overall. So it really has performance benefits. But it's also interesting as a design tool. You can express your intent when you have a service interface and you return a reactive type. By reactive type, I mean observable, publisher, promise, or something. You're saying this is not a local computation. You're saying this may go across the network. This may have side effects. And there are plenty of ways to do that. So now, my goal was really to tell you what it was about, but just very quickly, I'll show you different ways to go with reactive streams. So there are other alternatives to reactive streams, that if you're going with reactive streams, there is RxJava, which is the one I talked about, and it has a new version now that is compatible with reactive streams. It's called RxJava 2, it's the original name. And there is Reactor, which is also using the same approach. It's very similar, but written from scratch to be only about reactive streams. So your types, your reactive types in Reactor will be flux instead of a publisher of an observable. It says I have a flow of data. And mono will be like optional. It's 0 or 1 piece of data. It's a bit like a promise of an optional. And if you want a toolkit that provides more, there are two big things. There is Akka, which is more targeted at Scala, but that has Java APIs. I really don't think if you're using Java, it's the best choice. It's probably the most complete framework, but at the same time, it's not very nice to use from Java. And Vert.x, which is in Java and looks very much like Akka. So it's much more than reactive streams, but they have interoperability with their own projects, like Akka Streams is Reactive Streams for Akka, and Vert.x uses RxJava's tools APIs. And they provide tools for clustering and DB integration. And more than that, they have an abstraction that is called the actor model that goes much further than that. Though if you go to actors, you're changing the way you're building your application. It's okay, but you have to know that it's a big difference. So just to conclude, reactive could be an option. It could be blocking if you had one microservice and put Nginx in front of it and one database, and you scale horizontally because you need more throughput, just add more servers. But when you go microservices, you're going to be on both ends of those calls. And it's not going to be really much of a choice, because when you get cascading blocking calls, you waste a lot of resources, and it's not good for stability. As I said, also, the reactive types are useful to denote which methods are reactive. And you can tell developer it's better than documentation. This is potentially a non-blocking call. Or you can also wait and do nothing. But it's, there is a new project about having the same synchronous programming model on top of well, coroutines, which are basically non-kernel threads. So you could have fake threads. Of course, this will cost a lot, and we're not sure if it will make it, but that's a new open JDK project. And maybe in 5 years you get it. But even that day, when you get it, it will probably mean a more significant overhead than being with reactive, where you as low as an overhead you can get, right? So I hope it was clear. If you have questions, I think we have like 2 minutes.
Yeah, I heard you mention it, but you didn't have any charts about the push stream stuff from Osgi as a reactive stream-based model.
Yeah, so the question is about the Osgi push streams. So they are not implementing the reactive streams interface. They are on the reactive side. They are also streams, but they're not, part of the reactive stream implementation. So it's a very similar model. The big difference is on back pressure that you don't have the possibility to asynchronously request elements. You can just delay the producer and tell the producer, you will be allowed to send me something in that many milliseconds. And this works for some cases, like the push cases, but on the pull cases. And you must be careful not to block when you return the delay. The delay must be computed asynchronously as a mean. You must not really block, and then you can have bridges with reactive streams in a standard way because you're not blocking on that call. Anyone else? Okay, so thank you, and don't forget. Oh, well, as there was supposed to be a slide to vote +1 on -1, so you know what to do. Thank you.